Hello, everyone. Thank you so much for joining us today. My name is Shannon Holmes. I'm a medical physicist here at Standard Imaging. I have to say I'm rather excited about the talk today. I love the Scintillator. But before I introduce our speaker, I have just a little bit of housekeeping. We are recording the webinar today, so if you have to step out partway through, watch your email. You'll be getting a link for the recording this afternoon or tomorrow. So you can revisit that, or if you want to share it with a colleague, that's perfectly fine as well. The other thing I wanted to say is that if you have questions as Dr. Thrower goes through her presentation, please feel free to enter them at any time in the question dialogue in the GoToWebinar. We'll circle back to those at the end and have a good Q&A session after she's done with her slides. So without further ado, Dr. Sara Thrower is our presenter today. She completed her PhD and postdoctoral fellowship at MD Anderson Cancer Center. Her research right now focuses generally on advancing imaging for radiation therapy, specifically MRI for treatment planning in brain tumors. She is currently a second-year radiation physics resident at MD Anderson. So thank you, Dr. Thrower. We'll allow you to begin.
Thank you, Shannon. I really appreciate the invitation to present our experience with the W2 today. And I hope that everyone watching the webinar can get an idea from a user's perspective of how the W2 Scintillator works and is used in the clinic practically. As you heard from my bio, I am not I do not specialize in detectors or have not done a lot of research in detectors. So this viewpoint is going to be from just your average user of the detector. So I hope that you can take away something from this today. I'd like to start by acknowledging Standard Imaging and Dr. Holmes, of course, for providing the W2 for us to play around with, and my team at MD Anderson, Dr. Badar, Schuler, and Project Patti for helping me take all of the measurements in this presentation. So first, we're going to start with a brief introduction. I'm going to review flattening filter beams and ion recombination, and review the basics of ion chambers and the Excedrin W2. Then I'm going to go over how we took the measurements with the W2 and show our results, which is going to cover output constancy of the W2 and the ion chamber with dose rate, as well as our scanning measurements of PDD and profiles in small fields. Following that, we'll have some conclusions, and then we can open it up for Q&A. Starting with the introduction. In the days of 3D delivery, the goal was to deliver a consistent dose over a few large fields. Flattening filters were used to improve the dose homogeneity across the field. And so on the left, you can see that this is a schematic of the beam with the flattening filter here placed to flatten it. On the figure on the right shows the profile of the unflattened beam here in green, and in blue, the much flatter beam in blue. In addition to flattening the profile of the field, it also attenuates the beam, resulting in a lower dose rate. IMRT delivery uses many small fields rather than a few large fields, and this modulation requires many more MU to deliver the desired dose. So flatness is not as important in these small fields, and we can also now account for it with modern treatment planning software. And the higher dose rate from the flattening filter free beam can significantly improve the overall treatment time. However, this higher dose rate can affect the measurements of ion chambers we're used to using for beam dosimetry through an effect called ion recombination. So here's a schematic of a typical ion chamber. You have your outer wall made of some sort of plastic surrounding an a grounded outer electrode. And inside you have your inner electrode kept at a voltage. Typically for ours we use negative 300 volts, and it's filled with air molecules inside. When the radiation interacts with the air molecules, the electrons are collected by the inner electrode and counted by the electrometer. When the dose rate is high, there's a higher chance that the liberated electrons recombining with a recently ionized air molecule before they make it to the collecting electrode, and this results in an under-response at the electrometer. We can account for this effect through a correction factor called p-ion, which is measured using a 2-voltage method, and we will go over that in more detail later. In contrast, scintillating detectors are made of a solid material that converts energy of the photons into visible light. And it's transported via a fiber optic cable to an optical detector, so there's no possibility of recombination. And this signal should be linear with dose. We decided to test this hypothesis on our 10 MV flattening filter-free beam. And so this is a diagram here of the Excedrin W2 detector. It's available in the 1x1 millimeter scintillator. It's used in combination instead of your typical electrometer with a dedicated signal processing unit called the MAX-SD, and it combines the optical signal detection and the Shrenkov correction, which we will cover in a minute, into a single unit. And it allows the point dose measurement without any electrometers. And it does require this correction for Shrenkov light, and they use the 2-channel correction, chromatic correction, and this corrected signal can be sent to your water tank electrometer for small field scanning. To summarize, let's do a quick comparison of these detectors. Both are waterproof and can be used with your existing scanning and dosimetry equipment. The W2 has a much smaller active volume than even the CC01, and the W2 is solid polystyrene and tissue equivalent, whereas the ion chamber is filled with air, which must be accounted for to convert dose to tissue. Due to the lack of recombination effects, we would hypothesize that the W2 is dose rate independent and only needs to be corrected for the Shrenkov light ratio, whereas the ion chamber has multiple correction factors that must be applied, including p-ion, p-polarity, and shifting the PDDs to an effective point of measurement. However, the W2 is not currently calibrated by the ADCL and must be cross-calibrated with the calibrated ion chamber for absolute dosimetry, and it does show a small dependency on accumulated dose at about 1% per 10,000 gray. So it's important to understand how the linear accelerator delivers beam to understand how the dose rate will affect our chambers. The numbers presented here are based on the variant TrueBeam that we used in our study. On the TrueBeam console, the user can select a dose rate between 400 and 2400 MU per minute for flattening filter-free beams. The beam is then delivered in individual pulses, which carry an average of 0.13 MU per pulse. To decrease the nominal dose rate, the LINAC drops pulses periodically, effectively decreasing the pulse repetition rate. The dose per pulse is still 0.13 MU per pulse. And it's important to note that the ion recombination effect is only dependent on dose per pulse, or the instantaneous dose rate, since the ions have time to reach equilibrium before the next pulse. And that brings us to our methods. So how do we change the dose per pulse? One way is to decrease the distance between the source and the point of measurement. Our linear accelerator was calibrated to deliver 1 centigrade per MU at Dmax for a 10 by 10 field at 100 centimeters source to surface distance, or SSD. To increase the dose per pulse delivered by the detector, or delivered to the detector, we move the water phantom closer to the head of the LINAC. At 90 SSD, this gives us a pulse of 0.16 centigrade per pulse, which is approximately 20% higher And at 80 SSD, we see a 50% increase to 0.2 centigrade per pulse. So here's a schematic of our setup. For the ion chamber measurements, we used an IBA dosimetry, CC08 or chamber as our measurement chamber, and a CC13 as our reference chamber, which connected to an electrometer in the control room. For the W2 setup, the W2 worked with our standard Sun Nuclear 3D water tank. Here you can see we put it right where we would put the ion chamber, and it connects to the Max SD inside the room, which then connects wirelessly to your laptop through a browser in the control room. What we did to get it to work with our scanning tank was simply call it a diode so that no voltage needed to be applied. And you have the option of using a reference detector if you want to use a diode for the reference detector because it also doesn't require an applied voltage, then you can, but we chose not to because we just don't have any diodes that we regularly use on hand. So we measured p-ion and p-polarity at Dmax for all three SSDs to calibrate the ion chamber. P-ion is a correction factor for ion recombination that I mentioned earlier, which can be determined using the two voltage method according to this equation here, where your VH is the high voltage, VL is the lower voltage, MH is the measurement at the high voltage, and ML is the lower voltage. For our measurements, we used a -150 and -300 volts. P-polarity, or P-pole here, corrects for chamber polarity effects, and we don't expect this to be dependent on dose rate. So here are our results. We find that p-ion increased with decreasing SSD, or effectively increasing dose per pulse, as expected. And at the highest, or the smallest SSD and the highest dose rate, it nearly reached the limit of acceptability defined by TG51 of 1.05. P-polarity, as expected, was near 1 and showed no relationship with SSD. Moving on to the W2 calibration. The W2 does a two-channel chromatic correction. So the total signal seen by the W2 is here, and it's a combination of the actual scintillating signal combined with a small Shrenkov light contribution. And we can correct for the Shrenkov light contribution by calculating what's called the Shrenkov light ratio, or the CLR. And to do this, the optical light is split into green and blue color channels. And then you take a set of characterization measurements. You keep those to the scintillator constant, but just change the amount of optical fiber that's irradiated. And when you change the amount of optical fiber irradiated, only the Shrenkov contribution changes. You can also do a dose calibration where you can deliver a known dose to your detector, and the software will automatically correct all of your measurements to that known dose. We chose not to do this. So for the CLR calibration, the software on the Max SD walks you through this in a very, very clear and easy to follow procedure. You only have to do it once before you start your measurements. We use the two configuration method, where we have a minimum configuration, where we used our largest field size was a 30 by 30 field. So we used the 30 centimeters and by 5. And this is our minimum configuration. Then we simply rotated the collimator to get our maximum configuration, where more of the stem is being irradiated. The software then calibrates the CLR by looking at the difference in the blue and the green channels between the two configurations. then when you're taking your measurements, it applies this correction factor to get just the scintillating signal. So finally, we will cover our results. So for our dose rate constancy, just to review, we delivered 100 MU to each detector at Dmax at SSDs of 80, 90, and 100 centimeters. We're using our 10 MV flattening filter free beam and a 30 by 30 field to get the highest dose rate that we could. We normalized all of the measurements to the measurements at 100 SSD. And on the right here, you can see a plot of our results. And what's important here is that on the x-axis, we have increasing pulse repetition rate. And on the y-axis, we have increasing dose per pulse. The ion chambers are shown by circles. The W2 is in an X, and our theory measurements are in pluses, our theory calculations. We found that, as you can see here, the output was consistent with nominal dose rate for all detectors. So there's no dependence on dose or pulse repetition rate as expected. So we also calculated the theoretical output relative to 100 SSD according to TG71. In this case, our PDD is 1 because we took all of our measurements at Dmax. Our collimator scatter factor cancels out because all of our, we didn't change the collimator settings for any of the measurements. Then we used our phantom scatter factor measured in-house and the inverse square factor according to the field's size at the detector. The table on the right shows the theoretical increase in the output with SSD and the increase measured by each detector. The percent difference is shown in parentheses. The CC08 responded about 0.5% higher than expected, or less than 0.5% higher than expected for both SSDs, and had no correlation with SSD because we have already accounted for the effects of recombination that we would expect. The W2 responded slightly higher than expected, and there was some relationship with dose per pulse. And the reasoning behind this is still under investigation, but it could be due to how the pulses are processed. We also took some small field scanning measurements, profiles, and PDDs with the CC01, which is more comparable in size to the W2. And we still use the CC13 as a reference chamber. We use field sizes of 10 by 10, 5 by 5, 3 by 3, and 1 by 1 centimeters. These were taken at 100 SSD to chambers at Dmax. Again, we just used our in-house Sun Nuclear 3D scanning tank and the Sun Nuclear dosimetry software, which read in the data just as if we were using an ion chamber. It was able to be smoothed, normalized to maximum dose, and then of course we shifted the ion chamber curves upstream to account for the effective point of measurement. So here you can see that the PDDs agree very well between the two detectors for these small field sizes. And we can take a closer look at the 3 by 3, which is representative of all of the small fields. And you see here that overall, they agree within 5%, and they agree within 1% at about 2 cm depth. And this is probably because of the difference in how the surface dose is affected by the density and the size of the chambers. Profiles, we saw a similar, very good agreement between the W2 and the CC01. And we'll look closer at the 3 by 3 as an example. The largest differences occur in the penumbra region, where the dose fall off of the W2 is slightly steeper than the CC01, which is likely due to there being less partial voluming within the W2 because of its small size. So in conclusion, the Excedrin W2 is a new scintillator that's suitable for flattening filter-free beam dosimetry, and it can be used with your existing scanning tank equipment. There's good agreement between the W2 and small volume ion chambers for PDDs and profile measurements with typical measurement conditions. And we saw some over-response when we really pushed the dose per pulse, but even then it was less than 2%, and we're still under investigation to figure out why that is happening. And with that, I'd be happy to take any questions you might have, and thank you so much for your attention.
Thank you. That was great. If anyone has questions, excuse me, sorry. If anyone has questions, please feel free to enter them in that question dialogue in the GoToWebinar box. I was wondering if you could tell us a little bit about how difficult it was to get the W2 set up in your water tank, since you weren't using a standard imaging water tank. Do you want to talk about that just a little bit?
I'd be happy to. So it was pretty easy, except for the W2 is so much thinner than the housing on the ion chamber. We have custom printed or 3D printed holders for our ion chambers. So we simply wrapped it in some tape and it fit in the custom holders for our ion chambers. And we just put it in and aligned it the same way that we would with the ion chambers, with trying to put it at the surface. And other than that, getting then we pulling up the MaxSD software on the laptop through connecting to the IP address. I know you can plug it into your network as well, and you can simply do it that way, but because our network is so highly secured and we don't have a network plug in the treatment vault, we did it wirelessly, and that took a couple tries, but then once I got the hang of it, it was very straightforward.
Okay. Did you not have the sleeve adapter? We usually send a sleeve adapter, stem adapter with it that clamps onto the W2 and then matches basically standard scanning chamber stem sizes. Did we not include that in the loaner unit we sent to you?
I don't recall.
Okay.
It's probably in there, but
sorry about that.
Either it didn't work or like it didn't fit our custom in-house little holder.
Okay.
Or yeah.
Okay. That's funny. We'll check that if you want to do more research with it. Talk to me first, and we'll just make sure. I mean, that's something that we send to customers, so it's something that it'd be nice to make sure that it works with your system, because I know that not everybody is comfortable putting tape around a new detector. Yeah. There's a question from the audience. Did you notice any CLR fluctuations between the dose rates, or did you check the CLR at the different dose rates?
We did not check the CLR at the different dose rates. As long as you have the two configurations, the max and the min configurations, the only thing that would change is the amount of stem irradiated, but it shouldn't depend on the field size that you actually use. And it's a good thought to try it with the dose rate and see if that affects it. But no, we didn't. We only took it once.
Sure. I think the real underlying issue there might be if the Cherenkov spectrum changes based on those other dose rates, then that might have an impact on things. But something to look at in the future, I guess. Mm-hmm. Another question is whether you saw any decrease in the blue signal after longer irradiation times. Is that something that you observed?
A decrease in the blue signal. So we don't see the separate channel output. I'm maybe you can, but we just saw the final post-processed output, and so I didn't see a decrease over longer irradiations. And most of our irradiations were very short, 100 or 200 MU.
Sure.
Or we were scanning.
Yeah, that makes sense. And then there's a question about flash irradiation. Ken says, I'm not sure if this question can be answered. We're working on flash irradiation. Is that possible to use the W2 to monitor a flash beam at greater than 40 gray per second? It seems we'll have higher over response as dose per pulse increases. It could be a concern for super high dose rate cases. I guess I would answer that to say possibly, that it requires some more investigation, but definitely an interesting thought. Did you have anything you want to add?
Oh, definitely. You know, finding a detector for flash irradiation is always challenging. You know, there's film and TLD, but that's not the instantaneous readout that you want when you're trying to make sure that you've got your flash dose rates before your experiment. And this is, you know, no detector is perfect, but if we do figure out the dose rate dependence that might be there and correct for it, then this would definitely be a contender, I believe.
Sure. There's a question about really small fields. Do you think that you would still need to apply correction for Cherenkov even at those very small fields, given that the Cherenkov may be negligible because of the very small area, the fiber that's irradiated?
Well, I mean, even if the correction is 1, it's good to get the most accurate reading that you can. And it's so easy to take that CLR measurement. I would go ahead and do it. It might not be, I mean, like I said, we do P polarity for TG51, and it's often right at 1.000. So as you know, best practice is to always do all the correction factors that you can.
Be as accurate
even
as
if you
can.
expect them to be 1.
Yeah, and I guess I would add to that unless you're measuring a 1 millimeter field, you will always have some part of the stem that's being irradiated. So you'll always have some contribution from Cherenkov, even if it is a small contribution. And then would you mind sharing the method of how you scanned the small field using the scintillator? Was it step-by-step or was it a continuous scan?
So that's a really good question. We did it a couple times. We did a continuous scan in the end. The very, very small volume, it makes it really high accuracy, but also lowers your signal to noise ratio. So you have to scan a little bit slower than the ion chamber. And we also found that some of the smoothing effects on the W2 data, because we didn't have a reference detector to account for the normal beam fluctuations, and B, because of the smaller volume, they were noisy, and when we applied some of the correction factors, it actually altered the shape of the profile. But we found we did some trial and error and found a way to I think was it adaptive normalization to really, it did a really good job smoothing it without affecting the shape of the curve. And so even with the just scanning and not doing step by step, it would be probably, you're probably at a loss for your benefit and time ratio for very large fields, but anything under 10 by 10 to get those accurate small fields is definitely worth it.
Yeah. You had the picture of your alignment of the scintillator earlier. You had it positioned perpendicular to the beam axis, correct?
Right.
And you did that for both the output measurements and the scanning.
Correct. Correct.
And then there was a question about your data was for photons. Do you have any thoughts on what the difference in dose or dose rate response might be for electron beams?
That's a really good question. I don't off the top of my head know.
Sure. I would expect that it would behave similarly just because it's the electrons interacting with the plastic in either case, just like it's the electrons depositing dose in either case. But be a fun next project as well if you're looking for more projects, I guess.
Yeah.
Well, with that, I guess we're at the end of our half hour, and I really enjoyed your talk. Thanks so much. I guess if anyone has follow-up questions, send them to Standard Imaging, contact your salesperson, or contact us directly. Thanks so much for your time.
Thank you.
Yeah.
Have a great day.
You too.